In the last lecture, we discussed about Fourier transform, and we said that Fourier transform is important when you want to analyze any signal in a different domain. It's called frequency domain. And we came to know about two formulas. One was for Fourier transform. We said that it's from minus infinity to plus infinity, f of t e power minus j omega t. And here the signal f of t is aperiodic. This is not a periodic signal. So it means that we can take an aperiodic signal and we can transform that signal into frequency domain to see that for the same time domain signal, what happened with the frequency. And for inverse Fourier transform, for example, after analyzing the signal, we want to convert it back to the time domain, or if you have a frequency signal and we want to convert it into time domain, you can use this formula in which the differences we have 1 by 2 pi, and here you have minus, so here we will get a plus. We also solved one of example which was for rectangular pulse. So you can see that this rectangular pulse is aperiodic. It's not repeating itself. It is just between minus tau by 2 to plus tau by 2. And so this was the function that the rectangular wave has magnitude A within this time period, whereas it is 0 in the rest of the domain from minus infinity to plus infinity. And when we found the Fourier transform for this specific signal, we came to know that this Fourier transform was a sinc function. And we all know that sinc function looks like this. So if you put some value, for example, if we take a equals to 5 and tau equals to 0.5, we can plot this. Now you can see that here the key thing is that previously when we were representing a signal, we were taking n equals to 1 up to so on. Here the key thing is that we would try to see what is happening with the frequency, which is omega. It means that for a triangular wave in the time domain, it was just between these two instances, and this was the value. But you can see the frequency domain. So this triangular wave has a lot of frequencies inside it. So you can see that it has a DC value, which is 0. So at DC, this is maximum, 0 frequency. If we go towards positive frequency, you can see that how this is responding. So it means that if we talk about frequency domain, so in this signal we have big magnitude at 0 frequency. However, we do have magnitudes at other frequencies, but this signal, as the frequencies are going towards infinity or towards a higher number, their magnitudes are going down. So this is how we analyze a time domain signal into frequency domain. Then now moving further, here we're going to see that what are Fourier transform for some well-known functions. So we started this last time, but it was quick, so let's go through it again. Okay, so one of the functions is called impulse, and we define impulse as something which is happening for a very short interval, and it's going to infinite. So if, for example, I am striking a hammer for a very short amount of time, but the place where it is hitting, it's creating huge impact. And I given an example for pandemic as well. So here you can see that if you plot this function, this is impulse. So you can see that this impulse is at 0. It means that you can see that there is no thickness for this pulse. So if we draw this rectangle, so you can see that it has some width in the x direction. But here you can see that the width in the x is almost 0 because it is happening on a very, very small interval. So if I want to find area for this, which I can find like height into width, so area, or if I can say integral dt, if I want to find integral for this, it would be area height into width. So height, I know it's infinite, it's going to infinity. So height is infinity, whereas width is 0. So it means that it is something 0 times infinity. And 0 times infinity is undefined, we cannot define it. So for this specific case, we define it as 1. this is an identity for delta function that if we integrate it between minus infinity to plus infinity, its value is 1. So it means that here clearly we can see that the area is something, because infinity times 0 we cannot say what it is. It can be anything. So for this specific case we say that the area is 1. So it means that this is something we came to know. It is called identity for Dirac delta function. Now we want to find actually the g of w, that how the g of w looks like. So we know that if you want to find g of w, we need to use this formula, which is for the Fourier transform. So it means that g of w equals to minus infinity to plus infinity delta of t e power minus j omega t dt. It means that we need to solve this. Now what is the problem? The problem is that in fact this is not minus infinity to infinity. We can say that this is from 0 minus to 0 plus. Means it's staying almost in 0. So it means that I can put here 0. So it means e power j omega times 0. So this term would be 1. So it means that this thing is 1. So if I move it further, it would be g of w equals to 0 minus 0 plus delta of t. If I further go, I know that it has a value of infinite. So if I put infinite, 0 minus 0 plus dt. Finally, solve, even infinite is some number, so I can take it out. So it would be infinite times t, and limit is 0 minus to 0 plus. So indirectly, I can say that the limit is 0. So again, here you can see that it is 0. So it's mean that from this formula, again, we cannot define that what is the Fourier transform for a Dirac delta function. But we know something. What was that thing? And that's why we solved this identity. Give me a second, I guess I forget to turn on the recording.
Please be.
It's a good thing.
I suppose so. There's so many. So strange. Yeah. It's like
Okay, so if you have a look on this sinc function, here you can see that the sinc function is for a triangular wave. This means that it has some width. If I tend to reduce this width, I can say that it can be a Dirac delta function. So it means that if I will increase this width, this sinc function will squeeze down. You will also see it in MATLAB by plotting different functions, where you will see that if you reduce this width, it means that you reduce this tau value, you will see that it is squeezed. However, on the other hand side, if you squeeze this width, you will see that this triangular wave will keep on expanding. So from here, we came to know that if we keep on reducing the width and almost to 0, the Fourier indirectly would be a straight line. So from here, we came to know that if you want to find Fourier transform for Dirac delta function, we will say that it is equals to 1. So that's why we say that the Fourier transform for which g of w for Dirac delta function is equals to 1. And this we somehow obtained from making an analogy with a sinc function. Okay. Now another important function is another important thing here is to discuss about unit step function. So before going into detail, a unit step function is defined as for t greater than 0, it has a value 1 or something, it can be 2 or anything. For t less than 0 equals to 0. So if I define unit step function, it would be u of t equals to 1 for t greater than equal to 0 and 0 for t less than 0. So it means that we define unit step function in this way. If I relate it with Dirac delta function, I can do that. How I can do that? If I say that what would happen if we integrate Dirac delta function from minus infinity to plus infinity. So if I have a look on this waveform again, I can see that for less than 0, there is nothing. So it means that if I add zeros together, it would be 0. So I can say that for t less than 0, it is 0. However, as t is equal to 0 or greater than 0, it stayed at 1. So it means that at t equals 0, let's say it was 1, and then I keep on integrating it, and rest everything goes 0. So I can say that for t greater than equal to 0, it has value 1. So indirectly we can say that if we integrate the Dirac delta function, it would result as a unit step function. So there are two things. One is this is a unit step function. On the other hand side, you can see that this is a Fourier transform. So here we are just integrating it. We are not taking Fourier transform. However, in this case, we were taking a Fourier transform. So from this, we came to know two important points. One is, if you want to take Fourier transform of a Dirac delta function, it would always be 1 for all the frequencies. Whatever frequency is, it would stay at 1. However, if we integrate a Dirac delta function, this function would give us a unit step function. And that's why we written that the integral of Dirac delta function is called the unit step function. And same goes for the other side. So you can see that integral of delta of t is unit step function. If I take derivatives on both sides, so this integral would be cancelled by derivative, so you will get delta. So indirectly I can say that if I take the derivative of unit step function, this will give me Dirac delta function. So it's both ways. Right. Okay, now moving further. What if you want to find Fourier transform for an exponential function? But here you can see that the function we have written is e power minus at u of t. What does it mean? It means that this function is e power minus at times 1 for t greater than 0, whereas it is 0 for t less than 0, right? Because we previously defined what a unit step function is. So if I want to find Fourier transform for a function which is exponential times unit step, how it will make it different? Because I know that if I multiply e power minus at with a unit step, in the previous step we came to know that unit step is 1 for t greater than 0, is 0 for t less than 0. So that's why we can split this function into a new function. So that's why you can see that when we try to find the Fourier transform, it's e power minus at, e power minus j omega t. So this was the original formula. Then if we move further, here you can see that the limit has been changed from 0 to infinity. Why? Because I know that my function is only valid, which is e power minus at times 1 for t greater than 0. So that's why it's e power minus at, instead of ut I written 1, and it's from 0 to infinity, and rest this is the same. Then moving further, you can see that if we have same basis, we can add the power. So a power x times a power y, so it would be a power x plus y. So we can do same here, so you can see that base is same, which is e, so we can add the power, so which would be minus a t minus j omega t. So I can take minus common, it would be a plus j omega t. Finally, we need to apply limits, right? So it means that we need to apply upper limit and lower limit. So if we apply, first we take integral, so I know that for this, the integral would be e power minus a plus j omega t, and you can see that the integral is with respect to t. So if the integral is, in case of Fourier series, we always take integral with respect to omega t. Why? Because we say that its sine waves are repeating between 0, pi, and 2 pi. So it's more easy to solve integral with respect to omega t. However, in case of Fourier transform, since it is for aperiodic signal, we don't need to worry about period, so that's why we stay in time domain. Okay, so it means that if I take integration of this, the same thing would return. Then I need to take derivative of this and divide. When I take derivative of this, it would be minus a plus j omega, and this would come in division. Any confusion on this to anyone? Okay, it's simple integration. Same thing, divided by derivative of the power and divided. And here we have limit 0 to infinity. So it means that if you want to put limits, I can take this outside, minus a plus j omega, and limit is on t. So upper limit e, anything multiplied by infinity is infinity, and lower limit anything multiplied by 0 is 0. So it would be a plus j omega. What is e power in minus infinity? Can we solve e power minus infinity?
Is
So e power minus infinity means if I can write it e power infinity, right? I can simply divide it and minus will go off. E power infinity, e is 2 point something, so power infinity would return infinity. So I can say further infinity. And this is again an identity that 1 by infinity is equals to 0. Anything divided by infinite is equal to 0, which makes sense that if I divide a number with a huge number, so the result would be almost equal to 0. So that's why we can put this is 0 and e power 0 is 1. So it would be 0 minus 1. And finally we'll get it as a plus j omega. So it means that if we have an exponential function and if we want to find its Fourier transform, it would be simply a plus j omega. Or we can simply say that if here you have minus a, here it would become plus a. And similarly, if here is a, so here it would become minus a plus j omega. J omega is constant. Why? J omega would stay because it somehow comes from the transform formula. So j omega would stay like this. This a would always change depending on whatever you have here. If here it's a, at this point it would be minus a. Okay, now moving further. The next thing is that we want to see what happens. So far, if you see, we are saying if you have f of t, the Fourier transform is f of omega or g of omega, right? So we want to see that what happens if, for example, you have f of t and you found f of omega, and someone asked you that if there is a shift in the time. So for example, if there is a shift in the time, it's t minus t naught. So what would happen to the Fourier transform? So we should know, instead of calculating, we should know by formula that what would happen. So if I, before derivation, if I quickly see that if there is a time shift here, you can see that if I say, if I have a time shift f of t minus t naught, so it is obvious that the output Fourier transform would definitely have f of omega. If I don't know what is this shift thing, so if I know f of t and I know f of omega, g of omega for this function, if I know the Fourier transform, I can directly calculate the shift thing. So what would happen? This would stay the same, which is just for f of t, and you will get an extra thing which is e power minus j omega t naught. So again you can see that if I have a shift in time, how it will affect your Fourier transform, you will get an extra term which is e power minus j omega t naught. So this t naught would come from this t naught. And if there is a minus sign here, you will get minus sign here. And rest is f of omega. So it means that if you have f of t and you know its Fourier transform, and if someone asks you to find Fourier transform of the same function with a time shift, so you don't need to recalculate it, you can just take the actual Fourier transform for the function f of t and multiply it with this term, which will result, which would be equivalent as finding the Fourier transform for a shifted function. So here, this is Fourier. Now, if you want to really see how it is happening, so we know how we're going to move forward. We just need to take the function. Okay, so it means that if we have function f of t minus t naught, we know the formula, right? What is the formula? Formula is whatever function is, you need to put the function, multiply it with e power minus j omega t dt, and integrate between minus infinity to infinity. This is normal formula for function. Now let's solve it. How are we going to solve it? If you assume that this function thing is lambda, if you assume that t minus t naught is lambda, because we need to solve it, we will find a way to solve it. If you assume that this is lambda equals to t minus t naught, so from this, now we want to express our whole equation in terms of lambda. So we also need to change this t and we also need to change this t. So how are we going to do that? So lambda equals to t minus t naught. So if I want to find t, so t would be lambda plus t naught. One problem is solved. So it means that I can simply put, instead of t, I have put lambda plus t naught. Now the second thing is I also have to replace dt, right? Replacing dt is very easy. How? If you take derivative of this side, so it would be d lambda plus this t naught is constant, so for derivative for constant is 0. So it means that we can simply replace dt with d lambda. So we just simply took the derivative on both sides. So this we said it is d lambda. However, this is dt and this is the constant, so it will become 0. So that's why you can see that instead of dt, we can simply write d lambda. So now it means that we have slightly different equation which has f of lambda. Why? Because t minus t naught was replaced by lambda. Here t minus t naught, we want to replace it with lambda. So we calculated what is t. Sorry, here. So we put this value and finally we need to find dt. So we take derivative on both sides, and when we took derivative on both sides, we said that dt equals to d lambda, because this is constant, would become 0. Okay. Now, if we further look at this equation, so you can see that if we look at this part, it is e power minus j omega pi e power minus j omega t naught. So it means that if I do the same, base are same, so I can add, it would result me the same number, right? So it means that I need to split this. If I split this, I can write it in this way, which is, if I go back, is the same thing. Now you can see that if I see at this whole integral, this integral is with respect to lambda, right? Whereas this e has lambda, this e doesn't have lambda. So it means that this is a constant term, with respect to the integration, because the integration is at the moment on lambda. So it means that I can take this outside. So you can see that here I have taken this outside. Why? Because this was a constant, and the rest, what is left? F of lambda, this thing was left. So f of lambda, this thing, and finally it's lambda. So here you can see that what this equation shows me. This equation shows me that this is the Fourier transform for f of lambda, any f of lambda or f of t. So it means that this is your Fourier transform for f. I will write f so that we know that it is for original function f. It can be g omega, it's just a donation. Okay, so it means that this is f of omega, and now you have this extra term. So it means that we came to conclusion, if you have a time shift, so the time shift would result in a Fourier transform of the same function with an extra term, which is e power minus j omega t naught. But to find this, we took the help of replacing the variables with the new variables that we have considered. But even if you don't know the derivation, still it is fine, because this is our main objective, to find simpler ways to solve our Fourier just by taking these formulas. Okay, so this was for time shift. So if you have time shift, so we just need to take this with minus omega naught t, minus t naught, and we will put it here. Now another thing comes as frequency shift. What happens that if you have a frequency, so here what we came to know, if you have a shift in, so what would be the Fourier transform? However, here we want to see if we have shift in the frequency, what would happen to the corresponding f of t? What would happen to corresponding g of t, right? So again, this is not difficult. It's same as we have approached this one, but in this case, the function which was, we took f of t, so we use the Fourier transform. So here you can see that since you have g of omega and you want to find f of t, so you will have to use the equation for inverse Fourier transform. And you know the equation for inverse Fourier transform is this one. So if we use this equation and we somehow put shift inside this, we can get to know that what happens with f of t. So here what we have done, omega minus omega naught, here we have e power j omega t, but here you know that from the formula we have 1 by 2 pi. Again, if we do the same thing, just replace this omega naught with a different variable, finally you get to know that it would be f of t e power j omega naught t. So it means that if you have shift in the frequency and if you want to find time function, so if you know that for g omega the Fourier inverse is f of t, so you can easily find, and if someone asks to find omega minus omega naught for Fourier inverse, you can simply take f of t, you can take e power plus j omega naught t, and you multiply it, and you can say that this is the time domain function for this equivalent frequency shift signal. So it means that in frequency we take the same sign, negative goes here with the actual Fourier transform. In inverse Fourier transform, we take different sign here and multiply it with the original function for the g of omega to calculate the frequency shift. So these two things were related to frequency shift and time shift. Linearity property. Does anyone know what is linear or linearity property? What it says? Okay, so
like does that mean it's consistent?
It's consistent, yes. So f1 of t, if we say that the Fourier transform for f function, some function was g1 of omega, and for function f2 it's g2 of omega. Once again, even if you write it f2 of omega, it doesn't matter. The only thing is you need to use capital letters. Rest is the same. So it means that if you have f1 of t, g1 of omega, f2, g2 of omega. So Fourier transform, we say it's linear. How we check linear thing? We want to see that. So if you multiply function f1 with a, and similarly multiply function f2 with b. So we want to see just multiplying this function with a constant number, what happens to the Fourier transform. So it means that if we, before going to detail, if we think logically, it means that if I am multiplying a with f1 of t, b with f2 of t. So logically, I can think that for this, I can write something g1 of omega plus b, g2 of omega. Why? Because I am not changing the function, I am just multiplying a constant. So if I know f1 of t has Fourier transform g1 of omega and f2 of t is g2 of omega. So if someone give me that, I simply need to multiply it with a, so I can say, okay, it's fine. A multiplied by the actual Fourier transform would stay correct. But we can solve it using the formula as well. So you can see that if, for example, I need to find Fourier for this function, which is sum of these two with constants a and b. So now imagine that you have another function f of t, which is a f1 of t plus b f2 of t, and you need to find Fourier transform for this. So it means that I know formula for Fourier transform. Here comes f of t, and this comes from the Fourier. Simply, I can take this and multiply inside with both of them. So you can see that a f1 of t e power minus j omega dt. So it means that I have taken this term, multiplied with the first term. Similarly, I have taken this term, multiplied with the second term. So you can see that here is the second term. From here, again, we came to know that this is Fourier and this is Fourier. Why? Because f1 of t when multiplied by e power minus j omega t, this is formula for the Fourier. Right? From the formula, we know that we just need to put function multiplied by this, integrate, this would give Fourier. So it means that I can say this is g1 of omega and this is g2 of omega. So finally, so it means that Fourier transform is a linear transform. So if two functions has a Fourier transform, if you multiply some constant with those numbers, the final Fourier transform would be just the addition by multiplying with those numbers. So this thing is called linear property. That even if you multiply something with a function, its output Fourier doesn't affect, except that you will simply multiply those constants which will multiply with the function here, and you will get the Fourier transform. So this kind of property is called linear property. Any questions so far? Okay, now the next thing. Next thing is easy but slightly trickier. Duality. How do we define duality? So if, for example, you have a function f of t and it gives you g of omega. Duality means that if I simply replace their independent variable, for example, t with omega, so what would happen? So for example, for f of t, I knew the Fourier transform is g of omega. So what would happen if I say, what is g of t? So it means that if I was having a function e power minus at u of t, so I came to know that it was a plus j omega, right? We came to know. So here it says that if for f of t you were having g of omega, this one. So let's assume that now this was g of t, which is 1 by a plus j t. So what would be f of omega for this one?
So can you go over it with a dark color? You can't see.
Okay. So duality property means that if we have f of t equals t power minus at u of t. So we came to know that for this the Fourier transform is 1 plus j omega plus a. This we calculated a few moments ago. So what duality asks, duality says that if I replace it with t and I ask to find f of omega. So it means that what I have done, I have f of t and I found g of omega. So then I say that if, for example, I say this g of omega, now you can see this is a completely different function, right? So if I say, okay, I have this g of omega as g of t, so what would be Fourier transform? So we can find it easily. At the moment I can see it would be difficult to find Fourier transform, because if I put it in the same formula and go through proper derivation, it would be a difficult. But we can take some help from duality. So f of t is g of omega, g of t. So here we want to see that what would happen with f of omega. So here we want to see that what would happen with f of omega, but using dual. So now you can see that here what we need to find Fourier, right? For its dual. So it was omega, so its dual means its same function in time domain is its dual. So if I take g of t e power minus j omega t, now we are trying to move towards the f of omega. So this is g of t, then in the next step just multiply and divide by 2 pi. Finally, so if I multiply, divide by this, and finally if I get to this point, from here I get to know that this is f of omega, which is Fourier, but with a minus sign. So we have a minus here and we also have a 2 pi here. So it means that if you have a function f of t for which you know that what is the Fourier transform, and if someone asks to find the Fourier transform for its dual, so what we can simply do that, we can simply multiply 2 pi, we can take f of t and we can simply put instead of t, we can put instead as minus omega. So it means that for the same function, using the same function, we can find its Fourier transform for its dual. This you will see from an example that is here in the bottom. Okay, so imagine that your f of t was delta function. So here imagine that f of t was delta function. What is Fourier transform for f of t? For delta function, what is Fourier transform? We calculated in previous steps, right? 1, right? The Fourier transform for f of t is 1. So I can say that for delta of t, the Fourier transform is 1. Now, so now what happens is, it means that this side is f of t and this side is g omega. So now I am being asked to find g of t, and for this I am being asked to find the Fourier. It means that I have been asked that if this is your f of t, what would be Fourier? So from duality property, we came to know that if I am being asked to find for f of t, if this was f of omega and now this is f of t, so I simply need to take this one and replace this t with minus omega. So you can see that in here for 1, the duality property says that for 1, the Fourier transform is simply the function, which was the delta of t, put here, multiply with 2 pi and replace t with minus omega. And since delta function doesn't exist for minus, so that's why even if you put minus omega or omega, it's the same thing. So that's why we say that if you are having a function delta of t and its Fourier was 1, so if for example we take that Fourier as a time function and want to find Fourier transform again, so we can say that we can simply take its time function, put omega and multiply it with 2 pi. So in other words, so if you have a function f of t and you have a Fourier g of omega, and if you want to find dual, so you need simply swap the variable. So if I swap variable, this is g of t. So how you find g of t? simply take this f of t, replace t with omega, but also, sorry, minus omega, but also multiply 2 pi with it. So this is called duality property. As I said that this is slightly trickier to understand, but we will see it further by solving one more thing. Okay, so it means that we came to know if we have 1 and if we want to find its Fourier transform. From duality property we just came to know that if we have a function f of t equals to 1 and if we want to find its Fourier, it's 2 pi delta omega, right? From duality property we came to know that if the function is 1 and if you want to find Fourier, otherwise if you directly want to find Fourier for 1, you will not be able to find it using the formula, because in the formula you will get minus to infinity plus infinity, so you will not be able to find it. But here we take help from duality and try to find what is the Fourier for 1 if you want to find. Okay. So if I multiply this 1 with e power j omega naught t, if I multiply 1 with e power j omega naught t, and if I want to find Fourier again, what would happen here? You just, sorry?
So you're going to divide by j.
So you know here, okay, you know here that if we were having a function f of t, and if there is e power j omega naught t multiplied with this, what happens with the frequency domain? With the frequency domain, you can see that this is actually shift in the frequency. So if we go again here, so if we multiply 1 with certain thing, and if we want to see its delta omega, so simply we need to replace omega with omega minus omega naught. Again, you can see that here we wanted to see that if we have a frequency shift, how it will look like in time. It looks like in time as function times e power j omega naught t. If we go reverse, if we have omega naught t multiplied with a function, so how it looks like in frequency it would be shifted by omega minus omega naught. So same thing we are doing here. We know for 1 we have Fourier transform g of omega like this. If I multiply it with omega naught, so it means that if this was f of t and this was g of omega, here what I have done, I have multiplied f of t with e power j omega naught t. I just came to know that it would result as omega minus omega naught. So if I see here, the omega was this, so if I put, it would be 2 pi delta omega minus omega naught. So it means that if I have 1, if I multiply it with e power j omega naught t, it will shift the Fourier transform with omega minus omega naught. Why I am doing this? Because I am trying to get to sine and cosine, because it's very important that we know Fourier transform for sines and cosines. Any question on this? Any confusion? If you have any confusion, please ask so that I can move forward. So we have function f1, and we from duality we came to know that Fourier is this one. If you multiply with j omega naught t, and again want to find Fourier, we simply shift the frequencies in Fourier, and we will find the corresponding Fourier transform for this function. Now if we move further, we're going to move towards finding Fourier transform for cosine and sine. Right. So if you want to find for cosine, if you have cosine omega naught t, if I want to find Fourier transform this, at the moment I don't know what is Fourier transform for this. But I know that I can write cosine is Euler identity. This we know from the very beginning. That would be e power j omega naught t plus e power minus j omega naught t divided by 2. Right? This we know from the very beginning that this is how we can represent a cos signal. If I further split it, it would be 1 by 2 e power j omega naught t plus e power minus j omega naught t. If I say that I multiply 1 here, it doesn't affect this function, right? 1 is already here. Why I am doing that? I am trying to use somehow the property that I have just calculated above. So it means that if 1 is multiplied with certain thing, what would be the Fourier? 2 pi delta omega minus omega naught, right? So here you can see that 1 is multiplied here and 1 is multiplied here. The only difference is that here if you have plus omega, so you can see here it comes as minus omega. So plus omega okay, so it means that I just came to know 1 times e power j omega naught t is, if you want to write Fourier transform, this would be 2 pi delta omega minus omega naught. Similarly, if I want to write for this one, it would be 1 e power minus j omega naught t. If I want to find Fourier, this would be 2 pi delta omega plus omega naught. So it means that I know from duality property that these two hold, and if I can simply put them here, it would be 2 pi delta omega minus omega naught plus 2 pi delta omega plus omega naught. Finally, if I take 2 pi common, it would be delta omega minus omega naught plus delta omega plus omega naught. Any questions so far? So it means that if we want to find Fourier transform for a cosine signal, we can simply say that for a cosine signal, the Fourier transform is pi into delta omega minus omega naught. Omega naught would count whatever frequency is here in the sine. Similarly, delta omega plus omega naught, again whatever frequency is here. Any question on this? I know slightly boring, but yeah. Okay, so if I want to plot this Fourier transform, I can do that, right? For example, I know we know that if delta of t, so I can say that it has, so delta of t it's similar t minus 0, right? If I write delta or if I write delta t minus 0, it's the same thing. So it means that at 0 I have impulse, right? If I relate it with the similar thing, so it means that the Fourier transform of cosine, if I want to draw it here, so here you can see that here, like I said, at 0 I have a pulse, right? In this you can see that you have omega naught and omega. So it means that omega naught would be here and minus omega naught would be here. So it means that I have two pulses. I have two pulses. One is here and one is here. So it means that if I want to find the Fourier transform of a sine wave, for a cosine wave, I will see only two pulses. One is here and one is here. And this is aligned with the mathematics of cosine as well, that cosine has only one frequency which is on positive and it has only one frequency on the negative. So if we analyze sine wave in detail, it has only one frequency which is on positive side and one frequency on the negative side. And from this Fourier we also came to know the same thing. So it means that if we want to find Fourier transform for a cosine, it turns out as two impulse functions multiplied with pi. It means that we have two pulses, one at omega naught and one at minus omega naught. Okay, so You can see that if we draw the frequency spectrum for Fourier transform for cosine, we have one at minus omega naught and one at omega naught. And here you can see that the amplitude is pi, so that's why we said that it has pi amplitude. For sine, I will not repeat the same derivation, but only difference in case of sine, you can see that you have a j term here. Rest, more or less, it's the same, and also you have a negative sign here. So if I want to draw the same thing, you will see that it's pi by j, delta omega minus omega naught, then between we have minus. But again, we say that it has more or less the same frequency spectrum. Right. Any questions so far?
Just wondering, is there any theory in this module?
When AI will start, we will see slide.
What have you said?
He asked if there's any theory in this module.
Really? Ah.
Yes, so when AI part will
So
start, we will see some theory, but yeah, before that it's only maths, unfortunately.
It's gonna be artificial intelligence.
Yes, AI part would be some theory.
So the exam is gonna be combined in theoretical and practical.
Sorry?
In the exam, it's gonna be part of artificial and signal processing.
Yes, both.
Okay.
The first test, it would be only this part. It would
The
be,
face test.
yeah,
Face
it
test.
would be in 7 weeks. So most probably I will give you few questions.
So how's
this
gonna be
one.
the face test? How is it going to be? Is it going to be on BLE? Is it gonna be online?
Yeah, I was thinking to have it in class, probably give you only one question and you can solve it. It'd be easy. So that I could help you as well, yes.
It's like a test.
Yeah, you see.
It's
You
like
find really
everybody
easy.
Is there any
School
assignment in
days.
this module?
Sorry?
Any assignment?
Yeah, there are assignments. Yeah, I will give
How
it.
long is it for the face test? Is it 1 hour or half an hour?
How much you want? I will
I
give
don't
you
know.
my
To be honest,
time. Yeah.
it
So
depends on the question.
Didn't get subject.
we'll see. Don't worry. It would be easy, hopefully.
Hopefully. Wait.
Yeah, I will try to help you as well.
Week 7 is gonna be like 3 weeks time.
So it's 4th week, yeah. So probably in 7th week, yes.
I don't know how many years.
Okay, so moving a little bit further, it's not. I know it's slightly boring, but
It's not boring.
It's not boring, it's
yeah, it's difficult. Yes. So I would not ask you to do all these derivations. Even for the sake of understanding, I'm just explaining derivations. I could have just put a table and said, okay, for cosine the Fourier transform is this, but then it would come into your mind from where did I get. So it's very important that you just know if at some point in your life you need to calculate it, you know how to do that, right? But otherwise, if for example you know if you have Fourier transform for e power minus at, we know how we're going to calculate it. But I will never give you so much difficult things to solve which is beyond time or something. Okay, so now let's see another example which is called odd symmetry. We know that even symmetry is when something has reflection around x-axis, sorry, y-axis. When something is reflected about y-axis, we say that it is even symmetry. But when something is mirrored along the y-axis, we say that it is odd symmetry. So you can see that we mirror it around the y-axis. So it means that these two are in odd symmetry. So this is one exponential function. This is another exponential function. If for example I want to draw these exponential function to get that figure, how I'm going to do that? I know that this axis is time. So I can put different values of time and I can get this graph. For example, if I put t equals to 0, e power 0 is 1, right? So it would start from -1. And if I keep on increasing t, and let's say I go even further, and you will see that it will converge to in this direction. More easy to understand is sine, which is e power minus at. So if we have a look on this, if you put t equals to 0, you will get 1. It will start from this point. If you keep on increasing t, you will see that if for example you put t equals to infinity, if for example I put t equals to infinity, e power minus infinity, so 1 by infinity is 0. So it means that at t equals to 0, I will get 1, and if I keep on increasing t up to infinity, this form will go to 0. So it means that always you will see that exponential has such kind of curve where it starts from 1 and it keeps on to go towards 0. This is called exponential. And same holds for the other case. It's just that it is multiplied with a minus sign. And we also have a minus here. Okay, so it's just that this was one function, simply multiplied it with minus. So if you multiply it with minus, it will come into this side. So it means that these are two functions which are in odd symmetry. If you want to find Fourier transform for this, you can see that for t greater than 0, we have this function. For t less than 0, we have this function. So it's same as solving. We have solved so many questions where we are just splitting our integral based on our function. So we know that what is Fourier transform? Fourier transform is minus infinity to infinity f of t e power minus j omega t dt. So now function is between two limits, which is from minus infinity to 0, and there is another limit which is from 0 to infinity. So it means that we need to split this function into two limits. Minus infinity to 0, function has this specific value, so we have this one. Then for greater than 0, function has this specific value. And if we solve it like we done for simple exponential function, you will get finally it as minus j 2 omega divided by a square plus omega square. You remember if we want to find Fourier for e power minus at, what is Fourier for this? We just calculated, right?
Yes, the one.
A plus j omega, right? This we recently calculated. So it's the same function. So you can see that if we finally put limits, you will see that this is 1 by a plus j omega. So it's just that we need to put functions and we need to find the Fourier transform, depending on what function you have. Okay, now there is a function which is called sine function. This is not S-I-N-E sine, this is sine signature, you can say. This function is different than sin. Here you can see that it has one value for t greater than 0 and it has minus 1 value for t less than 0. Physically these signals mean, for example, if I have this unit step signal, it means that it can be anything. For example, button that I'm turning on or anything that was off and then I was turning it on. So this is physical interpretation. So more or less these have same physical interpretation. So if, for example, something was deactivated and then we activated it. So this is how we represented or related to the physical application. So if we want to find Fourier transform for a sine function, for a sine function, we can use something which we have done previously. If you put t equals to 0, it would be minus 1. If you put t equals to 0, it would be, or another way, if you put a equals to 0, you will get the equivalent in, so see, e power 0 is 1. So for the first case, it would be minus 1, and for the second case, e power 0, it would be 1. So it means that if you put just a equal to 0, we will get the same thing here. It means that if we put in this equation, if we put a equals to 0, our function f of t would be somehow this one. So it means that instead of finding and going through this whole thing, if I simply put a equals to 0, I will get the same thing, I will get this equation which is 2 by j omega. So it means that if you have a sine function, if ever you get a sine function, which is more likely that we normally get in many applications, this sine function, you can simply put Fourier transform as 2 by j omega, you don't need to calculate it. Then there is a final thing which is unit step function. As I explained previously, what is unit step function? It is 0 in this domain and it has one value. We haven't calculated the Fourier transform for a unit step function. So if we want to find it, how are we going to do that? So here we will take help from sine function and we'll move forward. And we'll do that, how are we going to do that? If for example, I know what is u of t. U of t is 1 greater than equal to 0 and 0. This is how we define unit step, right? True? Now, if I come to this equation, if I say that unit step, I have equated it with a sine function t plus 1 divided by 2. How this will work? See. If t is greater than 0, if t is greater than 0, sine function is 1, right? So it means that for t greater than 0, I can write u of t is equal to sine function is 1, 1 plus 1 by 2, so this is 1. So it means that for t greater than 0, I got same value which I was expecting, right? Similarly, for t less than 0, for t less than 0, unit step should be 0, right? Now have a look at here. T less than 0, this is minus 1. When I will put minus 1 here and plus 1, so this function would be 0. So it means that I can represent a unit step function with the help of sine function, and it will give me the same value as I expect for a unit step. So it means that there is no difference. I can simply put, I know this is sine of t, I know the transform for sine of t. So now I have this sine of t. I know what is transform for sine of t. For sine of t, I know the transform is 2 by j omega. So if I write here u of t, now I have represented it with sine of t plus 1 by 2, which is true as per definition, right? It gives me the same sinc function depending on time value. Okay, so it means that now if I want to find Fourier for this, I have two functions. So it means that, for example, u of omega equals to Fourier for first function, which is sine t by 2. I need to find Fourier for this function plus Fourier for 1 by 2. It means that I need to find Fourier for two things. I know Fourier for sine function, which is 2 by j omega. So I can put it here, it would be 2 by j omega, and there is 1 by 2 here. I also know what is Fourier here. If I take 2 outside, inside it would be Fourier of 1. I know what is Fourier of 1 from duality property. It's 2 pi. So it's 2 pi delta of omega. So it would be 1 by j omega. So it means that finally I will get as 1 by j omega plus pi delta omega. So these are some of identities where we get help from each other to find the Fourier transform for some of the known signals. So here what we have, we took sinc function, we represented it in terms of u of t, and finally moved towards the next step where I got sine function and a constant. So for sine function I know what is Fourier transform, for 1 I know what is Fourier transform, and this is how I get to know that how I'm going to find the final Fourier transform. Okay, so moving further, so now we want to see that what would happen if we have a time scaling. So if you know that if you have a function f of t and we know the Fourier for this function is g of omega, what would happen if we have a of t? So what would be g of omega? How the g of omega will look like, or what the g of omega I can. Okay. Right. So in this case, if we have a time scaling in any function, if we know the original Fourier series. So as I said that here, I don't know. As I said that the Fourier for f of t is g of omega. So if you have a inside, what would happen with this one? So it's simple that if I divide same a with the actual Fourier, and also instead of omega I divide omega by a. So it means that when we want to find Fourier transform for a function which is scaled by certain thing, we simply divide a to the whole Fourier transform and also divide the frequency of Fourier transform with a. And again we have a reasoning for this. I will not go into that detail, but the only thing important here is if we have a function f of at and if we want to find its Fourier transform, and if we already know what is Fourier transform for f, we simply take that Fourier transform, divide frequency by a, and divide the whole term with 1 by a. Right. Then comes differentiation in time domain. So for example, I know for f of t, the Fourier transform is g omega. So what would happen to this if we simply differentiate f of t? So in this case, if you already know g of omega and you want to find what would be the Fourier transform for its derivative, so now this is our new function and we want to find Fourier for this, which is unknown. So we don't need to do anything, we simply need to multiply the actual g omega with the term j omega. Again, as I said that for everything we have a reason. We go through their main formula and we try to see how it converges. So in this case, if we have a derivative, this thing helps when we have, for example, circuits where we have derivatives, where we have integrals. So we apply Fourier transform and we get easy analysis. So in this case, you can see that if we have a derivative of f of t and we want to find Fourier, so we simply multiply it with j omega times the Fourier transform of the actual signal, and you will get the Fourier transform of its derivative. Now, what would happen if we have derivative in the frequency domain? So if, for example, you were having g of omega, so if we have g of omega and for this the inverse transform is f of t, so what would happen if we take derivative in the frequency domain? So what would happen to its inverse Fourier transform? So again, in the previous case, you can see that you simply multiplied it with j omega. So now since you are moving from frequency to time domain, so you have to multiply it with t, j, same like this one, but here you will get a minus jt. So it means that if you have differentiation in time domain, you can simply multiply j omega with its frequency domain. And if you have a differentiation in frequency domain, and if you want to find inverse Fourier transform, mean if you want to find the original f of t, what you have to do, you have to multiply it with minus jt. So and this will give you the inverse Fourier transform, considering that you have differentiated in the frequency domain. We will do this triangular wave and we'll solve some question in the hopefully in the tutorial class. But in general, if I want to put remarks for
You took notes.
This one must. Yeah, I take notes. Need to start.
okay, so normally Fourier transform is used for frequency analysis, and this is mainly employed in communication system, communication engineering. However, some of the waveform, like we have seen previously, that if you want to find Fourier transform for a unit step function, you need to take help from sine function and so on. So it means that finding Fourier transform for some function like unit step function is not an easy task. So that's why for control system, for electrical circuits and so on, we go towards another transformation which is called Laplace transform. Another problem will be coming. So why Laplace transform is important? Because if we want to control something, or if we want to see, if we want to analyze electrical circuit, then we need to switch towards Laplace transform, and it is very important to study this as well. Laplace transform, you can say that it is an extension of Fourier transform. You have almost more or less same things with slight modification. Another important thing is, like we have seen, that the Fourier transform is applicable between minus infinity to plus infinity. This will not happen for the Laplace transform. Laplace transform will hold from 0 to infinity. And you have function, and then in the previous case you can see that you were having only e power minus j omega t, but now you will be having another term which is called e power minus j alpha t. So finally, if we say that the Laplace transform, it holds from 0 to infinity f of t e power minus s t gt. This s is Laplace operator, mean this belongs to s. In the previous case, if you remember, it was e power minus j omega t. Now this has been replaced with e power st, where s is alpha plus j omega. Now, why Laplace is important? Because in Fourier you can see that you have only j omega. Here you have an extra term which is called alpha. So it means that Laplace gives you a more detail about transient analysis, or it's more dynamic, whereas the Fourier transform gives you analysis which is missing some of the information that comes from alpha. So that's why we say that when we want to deal with control system electrical network, we tend to use more, we tend towards using Laplace transform. So Laplace transform has no physical significance. So if you want to see that how it is applied, can we see it physically? No, it has no physical significance. The only significance it has is it transforms one signal into a frequency domain. In Fourier, it was fully frequency domain, it was j omega, but here now we have another thing which is complex. Have you ever studied complex numbers? In complex numbers, we know that z equals to x plus jy. So it means that now we have a real part as well as we have imaginary part. So it means that now we have more enriched information. Laplace transform is mainly used as a tool for solving equations. So if, for example, you have a system and you write its mathematical model, then you need to solve that mathematical model, right? If, for example, if you have a circuit in which you have a mobile phone connected to its charger, so it means that for this specific circuit we need to know current and we need to know voltage. So in order to write voltage and current, we write its mathematical equations. But to solve those mathematical equations, it's very difficult sometimes to solve it in time domain. So if you have studied algebra or any other mathematics course, you will see that there are different methods we use for solving differential equations and so on. So Laplace is basically a very useful tool if you have differential equations. You can solve them with very less complexity compared to them solving it with other techniques. And lastly, it is very important that again, Laplace transform analyze your signal in frequency domain, more or less similar to the Fourier transform. And Laplace transform is used in signal processing such as data mining and machine learning, because it, as I said, that it studies your signal in frequency domain, so it will analyze which frequencies you want to keep, which frequencies you want to remove, and that's why we say that it has more mathematical applications, but it has no physical significance. As I said previously, there is an equal sign here. If you have a function f of t, if you want to find Laplace of function, it would be f of s. And how are we going to find it? More or less same as the previous case for the Fourier. Here you have function f of t. The only thing changed is 0 to infinity, and second thing which is changed is s. Previously it was only j omega, but here it's alpha plus j omega. So here you will write s. And again, if you want to find inverse Fourier transform, you need this formula. But later on we will see that mathematically it is almost impossible to solve this formula. We'll see why. So we will find other ways to solve the inverse Laplace transform. Why it is important to take inverse Laplace transform? As I said that if, for example, no one is from electrical, right? Anyone from electrical? Have you studied circuit analysis?
Yes,
All of them, right?
The basic stuff.
Very basic, right? Okay.
Yeah.
So, if I have a resistor, if I have an inductor, you all know this, right? Okay. And I know current is flowing in this circuit. If this is Vs, this is R, and this is L. If I want to write this equation, this would be Vs equals to I times R plus L di by dt. True, right? Okay. So it means that this is the equation for the circuit. Now, for analyzing this circuit, it's very important I find this current I, which at the moment I don't know. So it means that I need to solve this equation.
Your range formula.
Sorry?
Your range formula.
For this?
Yeah.
Yes, finally we solve it in some way, and we get a formula I equals to V by R 1 minus E something, right?
Your range formula, yes.
So how we solve it? There are different ways. More or less, say for example, you have studied these ways, those are not based on Laplace. But here with Laplace, it's very simple task to solve this equation. So what we do, we normally apply Laplace transform, we find current, but since we don't want our final current in Laplace domain, because we want to see it in time domain, because we want to analyze our circuit in time. So after applying Laplace for our simplicity, solving it, we need to take inverse Laplace transform. So what we do, how we solve this, we apply Laplace transform. I will not apply, I am just giving you example, and I find I of s. I will somehow find I of s. So, but I need I of t, so I will take inverse transform and I will find I of t. Why I am taking it to Laplace transform? Because solving this equation in Laplace domain is much easier than in time domain. So once I solve and find I of s, I convert it back to time domain so that I know what current is flowing in my circuit. So that's why it is very important that applying Laplace transform for the sake of mathematical computation simplicity but then taking inverse Laplace transform when I am done with my mathematical computations. Okay, now again, there are some functions for which we need to find Laplace transform, right? So in the previous case, you know that we found for unit step, which was something 1 by j omega or something, but it was very difficult to find. If I go back quickly, so you can see that here we found Fourier transform with the help of a sine function, and we came to know that I was having something like this, which is quite difficult. So if you want to find Laplace transform for a unit step function, so what is formula for Laplace transform? Function 0 to infinity e power minus st dt. So it means that I use the same formula, f of s equals to function e power minus st dt from 0 to infinity. And I know what is unit step function. Unit step function is 1 from t greater than 0 and 0 for t less than 0. It means that from 0 to infinity and minus infinity to 0. So it means that I have this one here. I can simply solve this integral. Let me solve it quickly so that. Okay, so if I want to find Laplace transform for u of t, it would be 0 to infinity f of t e power minus st dt. 0 to infinity. I know that unit step function has one value from 0 to infinity, so I will put it as 1 e power minus st dt. So finally 0 to infinity e power minus st dt. If I take integral, it would be e power minus st divided by minus s 0 to infinity. Right? This is simple integral. Now I need to apply limits, and limits is on t, so I can take 1 minus s common, e power minus s t, and limits will be 0 to infinity e power minus infinity minus e power 0. E power minus infinity, now we all know that it's 0. It will be minus 1 by s, inside e power 0 1, so minus 1. So finally it's 1 by s. So it means that solving the unit step function was much easier in Laplace domain than it was in the Fourier domain. So now we can see that this is for unit step function, the Fourier transform is 1 by s. So Laplace transform of u of t is equals to 1 by s. Now s we can put different values. Okay. Now how are we going to analyze it? So it means that the Fourier transform for a unit step function is 1 by s. S is frequency domain, right? We need to analyze this function. So let's analyze it. So we can put s equals to 0, s equals to 1, and we can put s equals to infinity. So if you put s equals to 0, so for one thing, first thing it would be Laplace of u of t 1 by 0. What would be answer? 1 by 0 is infinity, right? It means that S0 means zero frequency. Zero frequency means DC, right? Zero frequency means DC, a constant value, which is true in the time domain as well. So it means that if I put 0 S, which is zero frequency, it means that in time domain I know it's a constant value. So it means that it is understood from the Fourier, from the Laplace as well, that at zero frequency it has maximum amplitude. It means that it's a constant signal. It has no frequency, right? If I put infinity, it would be 1 by infinity. 1 by infinity is 0. So it means that if I put frequency as high, so this signal has no frequency, high frequencies. So it means that for high frequencies, it has 0 output, right? So this can easily be analyzed from its Laplace transform. So that's why I say that solving some of the functions are quite easy in Laplace domain. in this, as you can see that most of them are just formulas, and then you need to do your own calculations, right? So it's very important that you get your hands on integration by parts, differentiation, you know them on fingertips. And only then solving, I mean, more or less everywhere you can see it's just an integral, you are solving either two time functions multiplying with each other or one time function. So you definitely need to know about integration by part. Okay, second is function is e power at, exponential function. Again, we want to find Laplace transform. So Laplace transform of e power at, can someone calculate it? Please. Everyone, open your notebooks and just write this formula: 0 to infinity, e power at, e power minus st, dt, and find the answer. Just try to solve it. So that. And what would be the next step? Who will tell me in this? What would be the next immediate step that we need to take?
You break it down? You break it by
No,
parts?
there is no breaking down, right?
No, as in by parts, I mean.
Yes, you can do integration by parts, but there is another easy way you can do, right? Or no?
Just taking is, I mean, the addition of e.
The power loss.
E to the what is e minus 5t.
Yes, so you have same base, right? So you don't need to
Oh, you can add the
do
powers.
separate, right? So it means that you have a power minus x and a power y. So you can write them as minus x plus y. So you just need to combine them. Combine them and then solve it, then it will make your life easy. Anyone will answer?
It's like infinity minus something.
Yes, then you can take
It's
t
not
common,
right.
right? Because you will find
Should be
integration.
right.
So take t common, take t common. Yes, take t
I'm
out.
just thinking, if you have e to the, like a really big number, can that be simplified? You know when it was 1 over e to
No,
the
like this.
infinity, that turned out to
You can
be
see that
0, I think.
you
I
have
don't
e
remember.
power.
Remember this one?
but
1 over
yeah,
e
e will
infinity
stay here.
is
Now
0.
you need to take t common from
Yeah,
it.
because
If I take t
it's
common,
e
put a bracket.
minus
What would
infinity.
remain here? Would be
No, 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 no,
can
no,
never
no, no.
rewrite.
I mean, no, that is
So this is
that. That does the same thing.
You know what is integration.
But if it was positive,
E power.
then it would just be
So, you know that e power
that, right?
should
Yeah.
x plus
Which is
well, not over 1, it would be like that.
e
Which is infinity. Yeah, it's infinity.
What?
I mean, yeah.
Thank you.
It's insane. It's confusing to calculate. It should be. Oh, wait a second.
Anyone with answer? Okay, so
Is it minus 1 by a minus 5?
1 by
Minus 1 by a minus 5.
a minus s unit.
Yes. Oh, sorry, yes.
Okay, so e power at minus st, right? I can still further go e power minus t inside s minus a. Here you can see that I could have taken t common, right? But I have to taken minus t common because I know at some point I have to apply limits infinity. I know that e power minus infinity is 0. So that's why it's very important that you take minus t common. It doesn't affect your mathematical equation if you take t common or minus t, but it will help you solving your final answer,
Oh,
right?
okay.
And otherwise you will get an infinity and you will not be able to solve it.
Okay.
So the treated part, okay. Right? Now the rest is easy, you can solve it easily, right?
Yeah.
Yeah, we got stuck on the infinity part. We were like, okay.
That makes sense. Yeah, now I can solve it.
So what is your answer?
Minus 1 by a
There
minus.
should be no minus. What is your denominator, sir? 1 divided by?
A minus s.
Yes, this is correct. That's good. Anyone else got the answer?
Just a second.
If you multiply minus the denominator, it would be s minus a, right? Ah, yes. Did you get the answer?
It's a minus 1
It should be
under
minus s.
s minus a.
It should be
One
minus
sec.
s somewhere.
We do this.
It should be 1 divided by s minus a. Take your calculation.
Actually,
So if we take integration, it would be e power minus t s minus a. In the denominator, it would be minus.
They can't apply the limits in there.
You can take this thing out, minus s minus a inside e power. Upper limit is minus infinity, minus lower limit is 0.
oh,
So it would be 1 divided
Yeah.
Yeah.
No.
get this?
by s minus a.
I should
E power minus infinity, we know it's 0. 0 minus 1. So it would be 1 divided by minus s minus a. Inside it would be minus 1. So this minus would be cancelled with this. And finally it would be s minus a.
Yeah,
Yes,
I just got it partially.
Find your mistake. Find your
Yes.
mistake.
No?
it's the same as 1.
Oh.
1 by
There's a
minus.
minus outside.
Yeah, if you write it in.
Ah, yeah, that's what I got.
But normally we use this,
Yeah, but you
um,
need to change,
yeah.
put the minus.
We don't want minus on the top, so but you would also write this. So it means that if we have e power at, it would be s minus a. If there is plus, there is negative, and if we have e power minus at, then it would go at s plus a.
Thinking.
simplified Laplace for a cosine signal. Can you find this for a cosine signal? And we all know that finding for a cosine signal would be easy if we split it e power j omega t plus e power minus j omega t by 2. Now it's mean that we have two exponentials that we need to find Fourier for Laplace for. I want to find this is exponential and this is exponential. We already calculated the Fourier transform for exponential, right? So here what is exponential? J omega t, right? We know what is Laplace transform of e power at. What is this? We just calculated.
And
Just calculate s minus a, right? S minus a. So it means that now we have two exponential. One is so simply put it. So you know that this is Fourier transform. Sorry, Laplace transform of e power j omega t, and this is formula for e power minus j omega t, right? So it means that I can say this is Laplace of e power j omega t, and this is Laplace of e power minus j omega t. True? Is this correct?
Yes.
Yes. Okay. So it means that I can find it here e power j omega t. So from here I came to know that a is here, so here it would come as minus a, so it would be minus j omega. And if we have Laplace e power plus, so minus j omega t, so it would come as s plus. It's correct so far, right? It means that now we have two exponential, and we can solve them or we can directly put the formulas from there. So it would be 1 by 2 plus we can further solve it. It would be 1 by 2. We can take s here, which is s minus j omega, s plus j omega. So here it would be s plus j omega, and on this side it would be s minus j. Is it true, right? So
Yep.
we took the LCM and then we. Any confusion with this?
No, that's fine.
So the j omega would be cancelled with j omega.
And the 2 gets cancelled. The
Yes, 2s would get cancelled with 2.
mm.
So if I write it here, it would be 1 by 2. Inside it would be 2 divided by. You know this is simple formula, right? A plus
S
b.
square minus JW.
Yes, a minus b equals to a square minus b square.
Oh,
Right? Okay.
yeah, I just noticed.
Yeah. So it would be s square minus j omega square. True.
Yeah.
Right? And if I solve it further, this
J square is equal to
two
minus
we
1.
can-
Wait, sir?
Sorry, there was this.
Yeah, this.
Okay, so S divided by, okay, so this would be S here. Now we know this would be J square omega square, right?
Right.
So it would be minus J square omega square. But we know here J square is minus 1,
Right.
right? So it would be S divided by S square plus omega square. That means that the Laplace transform, these were quite easy. Than the previous one. S divided by S square plus omega square. Any question on this? Let's go to the lab now, and there we will solve some tutorial questions. But is
Which one? We can solve them.
Are we doing the triangle thing?
Transforms. Which one do today? Which is today?
sorry?
Transforms then.
Yes, it will be Fourier transform.
Transforms.